Hello everyone, welcome back to Exploring Quantum Physics. I'm Charles Clark, and in this part of the lecture we're going to take a venture into the realm of perturbation theory. Very powerful tool. In particular, we're going to look at it in the context of understanding the electrical properties of neutral matter. Okay, just to remind you, we're looking at the properties of a sort of a test case potassium rubidium molecule, which is of interest in ultra-cold atomic and molecular physics. And at the end of the previous part, we got to the realization that in the ground rotational state of the molecule, its dipole moment is oriented randomly, and so there's no net dipole moment. We want to orient it, and how do we do that? Well, we're going to apply an electric field to the system and see what changes that causes according to the picture of quantum mechanics. The tool we're going to use is called perturbation theory. It's a very powerful tool. Actually, in the form that we use it now, it was originally developed by Schrödinger. At least it was used in almost the very same form that we use it today in his early papers on the hydrogen atom, in which he deduced this, not just the spectrum of the hydrogen atom, but the response of that spectrum to an electric field. It's a very versatile and powerful tool of quantum theory, and also if you look at do a search on the phrase perturbation theory, you'll find that it is a very powerful tool of applied mathematical analysis in a more general context. So I think the lessons that you learn from working examples in perturbation theory are widely useful, no matter what your analytical interests are. Because here's the basic idea. Let's suppose that we're solving an equation of motion of a very complex form. Perhaps it's given by a Hamiltonian which has a lot of complexity, and we don't know how to solve that equation. So the idea of perturbation theory is that you try to find an approximation to that real Hamiltonian in terms of a Hamiltonian whose properties you know how to solve, and where the equations of motion that you're really interested in can be reached to some degree by an expansion in a small parameter. And so the idea is that you take a known Hamiltonian and its spectrum, and then you seek to develop in a systematic way the description of the new equations of motion in terms of a power series in a set of functions that can be computed iteratively. I should say that very often it's not necessary to go much higher than 1 or 2 in this series in order to actually learn very useful things. So we're going to work a couple examples. Here's the basic formalism. As I showed you before, we say, well, the Hamiltonian consists of the two parts, the known one, and then something else. And we're now going to focus on solving the time-independent Schrödinger equation by this technique. So we want to find the energy associated with this composite Hamiltonian. Now we do that by expanding both the wave function psi here and the energy E in terms of a formal power series in lambda, and then we just plug these two expressions back into the equation, and we match the powers of lambda in ascending order. So I hope you can see that. So we have h naught plus lambda v naught times psi naught plus lambda psi 1 plus etc. equals E naught plus lambda E1 plus etc. psi naught plus lambda psi 1 etc. And so let's match the powers lambda to the 0. So that means we take h naught times psi naught from here. There's no other match, and then on the other side we have E naught times psi naught there. So let's just run a reality check and see if that makes sense to you. So I hope you're persuaded by looking at it that at least this first equation makes a lot of sense, because it just gives one back the spectrum which one presumably knows how to control. Well, now let's see, how do we go up? Let's go to the next order. So we're taking powers of lambda to the 1 on each side, lambda to the 1. So from the left hand side, that's h0 times psi 1 plus v times psi 0 is equal to E0 times psi 1, and then E1 times psi 0. Okay, well, so far there's not much going on, just it's symbolism. So now let's what we do now is we take the matrix element, the bra of psi 0, with respect to this equation. Psi 0 on both sides, and so we now get this expression here. And I hope it's clear to you that when we look at this term here, that's exactly equal to this term by the Hermitian conjugation process. So we can drop these two terms, and then we get this simple equation for the first order energy correction. It's just the expectation value of the potential over the 0th order wave function. Now my friend, good friend and colleague Mark Edwards calls this the most used equation in quantum theory, which I think very well may be right. It's not the most written equation in quantum theory, which is the Schrödinger equation, but this is one which is probably solved more often than anything else, because it really gives one a very good guidance at an early stage on what you have to do, and it really just requires taking an integral of something rather than solving a spectral problem. So we're going to do some of that solving ourselves. Okay, so I guess you can see that there's some sense that you get in making some looking at simple considerations of standard problems when we have a trivial sort of potential that we apply. We see the perturbation theory describes that case well. Okay, so now we're going to go to the real problem, which is to try to understand the properties of a rotating polar molecule in the presence of an electric field. So here's our Hamiltonian. You see, it's the original rotational Hamiltonian with another term, which is the interaction of an electric dipole moment D with the electric field. This is the interaction from classical electrostatics, and so we can write this simply in polar coordinates in this way. And now I'm using these temperature equivalents just for convenience. So there's a sort of, keep in mind, this is just a temperature equivalent, saying, well, if you have an energy and you divide it by Boltzmann's constant, that gives a temperature. But it does describe the scale in a useful way. As you may recall, this equivalent temperature of the rotational motion of the ground state is something like 55 millikelvin. And now with using a sort of a dimensionless parameter of a field, which is a field strength of 1 volt per meter, then there's an equivalent electrical energy, which it turns out is very small compared to the rotational energy. So this is a sign that a perturbation theoretic approach will be useful in this problem, because we are using it to treat something that's small compared to the the underlying rotational motion of the molecule. And you might well imagine from a physical standpoint, if you have a molecule that's freely rotating and you just have a small brake to apply to try to slow it down, that when that brake is weak, it's not going to be that effective. So here we go on our way to solving this problem. We have the E0 vanishes. Here's the 0th order wave function, psi naught. It's just the ground state of a rotating molecule. So now we're going to evaluate the most used equation in quantum physics, the first order energy. It's the expectation value of the potential over the ground state wave function. And now you see this is just the potential is just the cosine of the angle with respect to the axes. So our expectation value takes this form. Now, I hope that through the exercises that you've done throughout this course, you've learned that sometimes you don't actually need to go through the mechanics of evaluating integral. It vanishes because of symmetry reason. And this equals 0 for a very simple reason, and that is it's an integral over all space of the cosine of an angle with respect to some axis, the cosine of this angle here. And well, obviously the cosine of that angle, whatever point you have here, there's another point where the cosine has an alternate sign. So this vanishes by symmetry, which is quite a common occurrence when evaluating first order energy corrections of this type, as we'll see.